Hi, I'm Professor David Farina. In today's lecture, we're going to be talking all about telescopes, specifically optical telescopes, ones that you would use with your eyes. Let's get started. Telescopes are kind of like a big bucket that collects light. So if you were to imagine a scenario where you forgot on a nice summer day, you had a pool party, and you left your drinks and the cups outside in the rain. And you also had a bucket like the one that you see down here, like a 5-gallon bucket. And you also have the swimming pool. And if it rains evenly across your entire yard, which of these buckets, the little cup, the 5-gallon bucket, or the swimming pool, would collect the most water? Well, of course, yes, the swimming pool would collect the most water. So just like a bucket collects rainwater, telescopes collect light. The bigger the telescope, the more light it's able to collect. That's its main function. So in our discussions today, I want you to keep that in mind. There are two main types of telescope. There is a reflecting telescope, and there are refracting telescopes. A reflecting telescope does just what it sounds like. It reflects light. Light is bouncing off of a mirror, and in this mirror, you can see it has a curved surface. So here's our curved mirror. And as light is coming in, we imagine light coming in from a parallel, very distant light source, like a star. So the light is coming in completely parallel. When it hits the mirror, it needs to follow the law of reflection. In the law of reflection, the angle of incidence, the incoming angle, has to be equal to the angle of reflection. Now, what happens here is on a curved surface, that principal axis, or actually I should say the normal, which is a point that is perpendicular to the mirror, it's going to be at different locations, pointing in different places. The focus is the point where all of those beams of light are going to be focused and place an image at that point. This is equal to the focal length. Now, the focal length is the distance between the telescope's mirror, where it's all focusing the light together. It's equal to 1/2 of the center of curvature. So if you could imagine that this thing is one enormous circle, this focal point is half the distance to the center of that enormous sphere. So light gathering power is one of the main and most important functions of a telescope, and it's fairly easy to calculate. So you take the diameter of one scope over the diameter of a second scope, and what you get is basically the area of that telescope. So just like pi equals the radius squared, or diameter divided by 2, which is radius squared. Here we have pi in both of these, so we can drop the pi. We have the same diameter equation to find radius, so we drop that part of it. They're both going to be divided by 2, and we're left with a very simple equation, the diameter squared. So we have the ratio of the diameter squared of these two telescopes, A and B, and what we can then do is determine how much the difference is in their total area. Now, a second power of telescopes is its magnifying power. Oftentimes, people have this unfounded idea that telescopes are important as magnifiers. Although they do magnify, it's not their primary function. Their primary function is to collect light and resolve it into a clear image. Magnifying power may be necessary on some objects, but objects like the full moon are actually pretty big. And some of the objects in the night sky, like galaxies, you would think that they're all small. The Andromeda Galaxy is actually 6 times as wide as the full moon is. It's just very dim. And so if we were able to either be in a very dark location, like Cherry Springs State Park, or if you were just able to have the ability to pan the sky with a nice set of binoculars, you would notice the Andromeda Galaxy is enormous. The tools that here at Astronomy Tools is a wonderful website, and it can help you to calculate things like these. That's what I have here. Now, to determine the power of a telescope, you take the focal length of the objective lens, that's the focal length of the telescope, divided by the focal length of the eyepiece. So what this allows us to do is we change eyepieces, and we can end up with a different magnification for different object types. This is really helpful. So I've chosen on this picture here 3 different eyepieces, and you'll notice that the first one up here, it's hard to read, I apologize, is 9 millimeters. Notice that the field of view, the area where this eyepiece is focused in on, is very tiny, meaning that you're zoomed in more. The next eyepiece up is a 26 millimeter, and this one is a wider field of view, not as well zoomed in. And the last one is a 38 millimeter, and you'll notice its field of view much, much bigger, less zoomed in. So what does this tell us? It tells us that the number here for the eyepiece, if it's larger, we have a wider field of view and less magnification. That comes directly out of the fact that the eyepiece is in the denominator of this equation. So if this is a really big number, our magnifying power is less. If this number, like this 9 here, is really, really small, well, that makes this part of the equation bigger, which means magnification is bigger. So that's how this works. So you choose different eyepieces for different uses. Now your telescope also plays a role in this. As I said, that's the focal length of the objective. Just so you know, this here is a telescope that has a 2,000 millimeter focal length, which is actually pretty long. It's a Schmidt-Cassegrain, a special type of telescope. So once again, magnification depends on the ratio of the focal lengths of the primary mirror and lens, or lens. The larger magnification does not improve resolving power. So this is important as well. So resolving power we're getting to in a later slide is the ability to see a highly detailed picture. Just because you're zoomed in does not mean you're going to see a highly detailed picture. And this gets a lot of people in trouble when purchasing a telescope, because they'll buy a very small telescope with a very high magnification, and all you end up with is zooming in on a really blurry image. Now, how do optical telescopes that are made of glass work? These are the refracting telescopes. What they do is, just like before, we have incoming rays of light that are all parallel from a distant source like a star. And you can think of the lens almost like a bunch of prisms. If we have a wider prism, we're going to have the light enter. It's going to be bent, which is the word refract, means to bend. So it's going to be bent, and as it gets bent, it's going to be bent less with a wider prism. I'm sorry, it's going to be bent more with a wider prism, a larger deflection angle, and it's going to be bent less with a more vertical, a less wide prism. And this makes sense if you think about it like this one in the middle. If you have no width at all, or if it's very straight up and down, then the light just passes straight through without being refracted at all. It's coming in directly perpendicular to this piece of glass. Now, the question we need to ask ourselves is, why is refraction happening? Okay, so what's happening here is that the light is coming in air. It's transitioning into a new medium, and what I mean by medium is it's a different substance. And this substance allows the speed of light to move more slowly. And as the light moves more slowly, that means that the light is going to bend. And when that light bends, it bends toward the more dense medium. So in this case, the glass, it hits, it bends towards the more dense medium, and then as it exits, it deflects backward again, and then away from that more dense medium on its way out. So we've got light bending, and the reason it's bending has to do with the speed at which it moves. So the speed of light in air is less than the speed of light, it's more than the speed of light in glass, which is less, it's slower. So that's why it's bending. So all a lens is a bunch of different prisms, effectively, that are stacked on top of each other, and each of them is designed to bend it toward one focal point. Now this works in some ways that are kind of interesting, and we'll talk about that in a bit. Now with a telescope, we also need to realize that sometimes light sources might be having some shape to them, excuse me, like this comet. So we have our comet, the light source from the top of this comet is going to hit the top of the mirror, and then it's going to be focused. Notice the yellow arrow here, and notice it gets its focal point here. Light from the top of the source hits, that was light from the top of the source. Light from the bottom of the source, in purple, hits and goes to the top. So, and light from the center, of course, focuses in the center. So at each of these different places, we end up with an image that is upside down. Okay, so let me just have you follow again. Light from the top goes to the bottom. Light from the bottom goes to the top. And this is going to cause an inversion of our image. So here are the basic two designs. We've got a basic refractor. Starlight enters, it comes to a focus, and then it's passed through into an eyepiece. The second type is a Newtonian reflector. So Isaac Newton developed this. The light, once again, comes in parallel, hits the mirror, which is a part of a curved surface. It hits, it would go to this prime focus. However, we place a small secondary mirror in the light path, which then bounces the light back to the side and then through an eyepiece. Notice the focus of this point right here is what we're looking at. And all we're doing when we zoom in on our eyepiece is we're zooming in on this little tiny mirror here. So this is actually what you're looking at. You're looking at the little mirror. Now, there are many different designs of optical telescope. So we've got a number of them here. Different focus points. Some of the telescopes that we use for imaging, not so many that we use for our eyes, but if you wanted to put a camera at the focal point, you could take a picture. So we've got the prime focus. We've got another prime focus here. We could also have out the side with the Newtonian. We could have a Cassegrain focus, which is out the back. Or we could have this Nasmyth focus out the side. This one here doesn't have too many applications for amateur scopes that you would see in your backyard. This is more of an observatory class telescope. These, however, a Cassegrain, a Newtonian, and just recently some of these prime focus imaging scopes are starting to hit the stores. So many of these options are out there for the consumer. One of the main problems with a refracting telescope, or disadvantages to it, is something called chromatic aberration, which is a fancy word for that the light coming through a lens depends, the location of the focal point depends on the color of light that's being passed through the lens. So with white light, for instance, which is going to have all of the different colors of the rainbow, it's going to have blue focus here, yellow focus here, and red focus way out here, which means you cannot have one place to look at with your eyepiece without getting something called chromatic aberration, color fringing. Now, an achromatic lens is a corrector lens. Notice now you have two lenses, and what that can do is either bring red and yellow together, or it can bring yellow and blue together. But in order to get the best possible image, you need an apochromatic telescope, which has 3 or even 4 lenses in order to bring all of the different colors of light together. And this sounds like it's getting very expensive. And you're right, it is. So every time we add a corrector lens, the telescope becomes increasingly more expensive. Modern observatory class telescopes are reflectors. And this is primarily because of the problems with going to very large lenses. So the first problem with the lenses, as we just discussed, is the refraction is wavelength dependent, and that you have to have these very complex lens systems to truly get color fringing or that chromatic aberration to go away. Second part is that some of that light that's passing through the lens is absorbed, and it's as a result not as efficient in some ways. Third, these lenses become extremely heavy. So we really need to be careful as we go bigger that the lens actually can sag under its own weight, and that means it's being distorted. And finally, these need to be of the utmost perfect surfaces. And what I mean by that is that the actual shape of the lens is what's causing the image to be formed. And if that shape is off by even just a little bit, it makes big problems in our ability to see for making our images for our astronomy. So lenses are not the most ideal thing for observatory class telescopes as a result. These are some of the pretty neat observatories that are out there. These are observatory class telescopes. The Keck telescope is actually 2 different telescopes, the twin Keck, and here they are. They're on top of Mauna Kea in Hawaii. For scale, this is a person in the very center in orange. These are enormous, enormous mirror systems, and you'll notice that they are of the segmented mirror type. So they're basically taking one little segment, and each of these segments of the segmented mirror are going to point towards that focal point and produce a single image. You'll notice that there's a second type, floppy mirror, and in both of these cases we have little thrusters that are underneath the mirror, that as we turn the telescope we can change the thrusters and keep the shape of that mirror in the correct and ideal shape, because it does have mass and it will sag under gravity, and so we need to be careful. These thrusters, this is called active optics, and it's very important to modern telescope design. Now this is the biggest observatory that's planned, the European Extremely Large Telescope. This is an artist's rendition. Just to give you a sense of scale, these are automobiles down here, these are cars. So this thing is enormous. You can think of this as like a size of a football stadium. It's that big. Now, what do I mean by taking pictures? I don't mean with film. We're talking about taking pictures with something called a charged couple device. This is very similar to what you're using in your cell phone camera, and it's just a data chip that collects light. And this electronic device can be uploaded, the image can be uploaded to the computer immediately, and image processing is where most of the work is done these days. All these do are basically counting the photons, as you can see here. So we have 7 would be a higher count, 9 would be even higher, and then we take that information and we assign a brightness to that in our image. So each of these zeros here, these would all be black, and you can see here is black. There's no photons hitting it, and you'd have 1, 2 objects. So image processing, as I said, is where all of the work is done. So our raw data out of our computer might look something like this, but after we manipulate it, we're talking like you would in something like Photoshop, but for astronomy specifically. You can use Photoshop, actually. We can take our image that looks like this and we can turn it into a much more detailed and much more refined picture. Now, where do you go to look through a telescope or to do this type of work? Of course, you want to get away from the big cities. So this is a light pollution map where you can see that in blue, all of the big cities are obvious. So we've got here, of course, Philadelphia, Baltimore, DC, New York, Boston, this whole stretch here along the East Coast. We've got Detroit, and we've got Chicago. We've got places along the Great Lakes. We've got this huge line from here to the east over of a lot of light pollution. But then as soon as you go west of the Rockies, you can see huge swaths of land that are extremely dark. Now, we've got in Pennsylvania a place right about here called Cherry Springs State Park. It's one of the darkest places on the East Coast, and it is recognized as an International Dark Sky Association park. This means that we are protecting it from light pollution. So that's quite a neat place to go. You can actually see your shadow with starlight on a moonless night. It's amazing. If you have questions, please shoot me a message and ask about it if you're interested in going. Now, of course, the higher up we go, onto the tops of mountains, for instance, the less atmosphere we have to deal with. Atmospheric turbulence is a big problem. It's called seeing. And so if we can get above the majority of the atmosphere, we get clearer pictures. So away from light sources and higher up. Now, of course, what is the best place to take a telescope? Of course, it would be outer space. So here's a picture that I think is pretty neat, an artist's rendition of, moon base, where we're doing observations, and here's some astronauts looking through telescopes, the optical telescopes. We've got some radio telescopes, and the moon might be one of the best locations for us to do our astronomy because, quite frankly, we could set up a base, have permanent residence with astronauts, and maintain the telescopes, and we have really good seeing because there is no atmosphere on the moon. And it's, of course, very dark. So this was our lecture today, all about telescopes, specifically optical telescopes. I hope you enjoyed, and I look forward to seeing you back. If you like this video, please make sure you hit like and subscribe. If you'd like to find out every time I make a video, click that little bell at the bottom. And have a great and stellar rest of your day. Thank you.